Hey everyone, in this video we are going into practical side of spherical harmonics in TouchDesigner. I will show you the full workflow, all the components and how to use them in TouchDesigner. And a quick note before we start, all tools I'm showing here are available to download for free on GitHub or on my Patreon. And if you like it and you want to support the project and future development, you could do it on Patreon. Later, I plan to release more ready-made examples for paid subscribers. This is a practical video, so you can use the system right away. But the theory video explains why it works and what these coefficients actually mean. So at some point, I recommend you to watch this theory video as well. Also, before we go any further, I want to mention a couple of limitations of the system. First is the system is for diffuse light only. It works well for the soft gradients, ambient structure, and the broad directional light. It's not meant to store sharp reflection, glossy highlights, anisotropy, or other high-frequency lighting detail. And second, the current version doesn't account for shadows or for occluding geometry between the light and the probe. So if geometry stands between the light and the probe, this blocking doesn't evaluate it yet. Okay, now for the workflow. I split the components into three groups. First, the generators and calculators. This creating the lighting data and write it into probe grid. Second, modifiers and analyzers. This let us reshape the field or extract data information from it. And third, visualization and rendering tools. This convert the probe data into something that material shaders could use. Let's start with generators and calculators. First, we need the probe grid. You can bring your own grid with regular grid pop, or you can let the component create the grid internally, if nothing is connected to the probe grid input. The main parameter here is the resolution, how many probes you have along each axis. I usually start with something like 8 or 16. It's often enough to make a field look smooth while it's still fairly cheap. Later, when we get to point lights, I will show how this resolution interacts with the quality and the performance. Okay, the first generator is the simplest one. It doesn't calculate light from explicit light sources. Instead, it writes the procedural lighting pattern into the probe grid using mathematical functions. So this component is less about realism and more about giving you the simple example of how the generator shader can write the spherical harmonics data directly. You can switch between the modes, look at result, and treat it as a starting point for your own experiments. And this is also a good place to mention something important. Along with the tools, I also provide the long reference documents that explains how these shaders are structured, how calculations are organized, and how to add spherical harmonics light into your own shaders. I do not really expect most people to read this whole document manually from start to finish. I actually recommend to give it to AI assistant, large language model, or coding agent, whatever you use, and ask it to help you or to adapt the shader to your needs. Or if you prefer, you can also use your natural intelligence and read and understand everything by yourself. Okay, the second generator is a 3-sun atmosphere setup. It treats the probe like a small planet that with 3 virtual suns moving around it with different speed and orbits. Each sun has its own color, and those colors can also change over time. Again, this is not really meant to be a general purpose production tool. It's here mostly to show that the light field can be generated procedurally instead of calculating from the light sources. Next is the environment map calculator. This component encodes a static or animated HDRI environment map into probe grid. This two calculation mode, exact mode, integrates the full source texture and gives the most accurate result, but it can take noticeably longer. depending on the text resolution. Monte Carlo mode uses a chosen random number of samples instead, so it can run much faster and much more usable in real time. A practical workflow here is to switch to exact mode once to find how the ideal result should look like, and then go back to Monte Carlo and find this number of samples that good enough match for your setup. Another important parameter here is HDR radius. Instead of rendering, the environment light behaves like it's infinitely far away. If you set here the radius very large compared to the side of the probe grid, like here, this calculator behaves the similar way. But if you make the radius smaller relative to the grid side, different parts of the volume starts to see the environment differently. So the light field becomes less uniform across the space, which can sometimes give you more interesting result. Next, we move from generators to calculators. The spherical light calculators takes two inputs, the probe grid as usual and the set of light points. These are not just zero size points. Their physical radius come from the point scale attribute. If the radius is 0, the signal is very sharp, more like a point light. If radius gets bigger, the directional response becomes softer and more wider. So the same calculator can be used both for tiny lights like fireflies or LEDs, and also for the much larger glowing sources. The most important practical setting inside this calculator is a neighbor pop. This decides which lights are actually considered for each probe. You set the two things here, the maximum number of neighbors and the maximum distance. In most cases, I just include all input sources as an expression here, basically all the points from incoming node. And I control performance mostly through the maximum distance instead. This works together with fall-off radius. The fall-off radius defines the attenuation curve, and roughly speaking, 4 times that fall-off radius is where the light is already lost about 94% of its intensity. So, using the 4 times the fall-off radius with an expression as a max distance is often a good default and speed-quality balance. It's not a strict rule. If you have a lot of particles or a lot of lights, the remaining contribution from this slight few percent can still add up and become visible. So use it as a starting point and adjust it based on the look you want and the performance you have. The next calculator is the line light calculator. It works on the same general principle as a point light calculator, and neighbor pop setup and fall-off distance behave the same way. The difference here is only the source geometry. Instead of points, we use lights. The shader evaluates each line segment as a continuous emitter by finding the closest point on a segment for each probe. You can use regular open or closed line strips, and also text pop in the line mode if you want, for example, a glowing neon letters. And the result doesn't depend much on how densely the points are packed along the line. Here, for example, the points along this rounded square are not distributed uniformly. For the line calculator, it doesn't matter because it reads the segments continuously, so the light intensity stays the same over the whole line. But if you feed the same point arrangement into spherical light calculator, the result changes much more, because every point acts as its own separate emitter, so the intensity wouldn't be uniform. In the spherical light calculator, intensity is stored per point in the alpha channel. In a light calculator, it's also read from the alpha, but the useful way to think about it as a total strip intensity. So two lines with the same length should give roughly the same total light, even if one is represented by many more points and the other just by few. That makes the line emitters a lot more comfortable to use, in my opinion. And that covers the main calculator section for now. Next is the modifier section. One of the nicest properties of spherical harmonics is that as long as probe grids match, you can add together the coefficient from different generators or calculators and get one combined result. So if you have one generator creating, for example, background field, another one coming from large light sources, the third one from tiny light points with different parameters, you can then combine all together and represent it as a one probe grid. If you want to assume two different spherical harmonic fields, your first instinct might be to jump into mathmixpop and do it there. But in practice, this usually is not very convenient, because you would need to write formula for each of 9 spherical harmonic attributes. A much easier way to combine several fields into one is to use blend pop. And the blend pop is useful not only for simple addition, it also has different blending modes, including proportional addition or others. So for combining spherical harmonic fields, it's usually much easier to use than mathmixpop, while mathmix still gives you a lot of different functions to experiment with. And I really encourage you to experiment with mathmixpop or other prop operators, because in the end we're just manipulating the data that's stored inside the pop attributes. And there is a good chance that many standard pop operators can do something interesting with spherical harmonics data. Also, I made dedicated modifier components for a few operations that are less convenient to build manually. The first one is rotation. It rotates the directional content of the whole field around the chosen axis. So if the light is already encoded, you can still rotate the encoded field afterwards, and it would be mathematically correct. The next block is easier to understand if you already watched the theory, but even without that, you can treat it as a creative control panel. The basic idea is that you can adjust color channels separately, and you can also adjust different spherical harmonic levels separately. So you can boost or reduce broad ambient attribution or directional gradients only, or high-level detailed diffuse structure from the level 2. A simpler way to think about it is like a channel mixer combined with layer controls. You do not need to understand every detail right away, you can just experiment and find the look you like. And the next important control is sigma windowing. When the light signal gets too sharp, for example, with a very strong localized source, the reconstruction sometimes can produce visible artifacts, like ringing, fail-through gradients, or unstable transition between the probes. Sigma windowing is a standard trick to reduce that. It's like a soft filter on high levels. Usually you need to set some small amount. If you start seeing such kind of artifacts, this is the first slider you can try to reduce it. And after that, there is a simple HSV adjustment block. This is exactly what it sounds like: hue shift, saturation, and value multiplication for the light field. The hue adjustment works the same as the HSV adjust top. So the 0 and 360 degrees give you the same result. And another component I include is the analyzer. It estimates for each R, G, and B channel the direction from which the strongest light is coming, and writes the strength of this directional signal into separate attributes. That means you can use the lighting field not only for shading, but also as a data for drive particles, geometry, or other systems. One important caveat is this analyzer is intentionally rough. It uses only the first directional level because it makes it much cheaper to calculate. So do not treat it as an exact reconstruction of the light, it's just lightweight directional metadata. Now let's move to the rendering side. Before we get to the materials, we need to convert the probe data into 3D texture. The reason for that is performance and flexibility. Sampling a 3D texture is much cheaper than indexing data from the pop buffer, and 3D texture gives us trilinear interpolation between the probes for free on GPU side. And on top of that, once data is encoded into texture form, you can apply any top operator to it, which open up a lot of additional options. So even though it looks like an extra step, it's actually both faster and more useful than reading directly from the pop buffer. I distribute the 27 coefficient across 9 RGBA 3D textures in a way that preserves R, G, and B grouping. In theory, all of them could fit into 7 textures because 7 times 4 is 28 channels and we need to store 27. But that would make the structure less clear and harder to manage and understand. The 3D texture resolution matches the probe grid resolution directly. Now to the materials. I prepared 3 main materials you can just copy into your setup. There is version, the normal map font version, and PBR. And this is also a good point to remind you that all tools, materials, and helper components are available for free on my Patreon. So if you want to use this 3 material setup, you can just download and copy paste from it. But Patreon support is always appreciated, and also you can hire me as a freelancer to help to adapt to you this approach to your needs. Now back to materials. The font material is the simplest one. It's based on the standard font workflow, and after the regular light components are calculated, it samples the 3D probe textures and as the diffuse contribution reconstructed from the spherical harmonics. To make this material works, you need to reference the probe texture samplers in the mat and provide the required uniforms for the probe grid in a uniform section. If those are missing, the material will not know how to sample the field directly. The normal map material works the same way, but now the decoding uses the normal map. This matters because when we reconstruct the diffuse light from the probe data, the result depends on normal direction we pass into evaluation function. So if the normal changes, the diffuse response changes too. That's why the normal mapped version is useful. It lets the same encoded light field react to the surface detail differently without changing geometry itself. The PBR material is similar in spirit, but here the spherical harmonics is used only for the diffuse component of the shading. This setup is not trying to represent reflection, metallic response, or glass specular with the spherical harmonics. Those parts are still handled separately, and material use the encoded probe field to contribute only in the diffuse lighting. Also, as a reminder, I provide the long shader reference document I mentioned earlier, which is useful if you want an AI assistant or a coding model to help you to adapt these materials to your own setup. And if you don't want to edit the shaders at all, there is another option. You can build a normal rendering setup the way you usually would in TouchDesigner, then drop this render pass component, tell it which render top to use and which camera. And it will render only the clean spherical harmonics diffuse contribution as a separate pass. Then you can combine this pass with your normal render however you want. For example, using composite top or any other compositing setup. So this gives you a raw diffuse result as a separate layer. And finally, here is one more variation I want to show. Sometimes you don't need a probe grid at all. Instead, you can store the spherical harmonics coefficients directly on the geometry itself. For example, in a particle system, calculating and storing harmonics on the particles themselves can give you more accurate shading afterwards, because you are no longer interpolating from the nearest probes. Also, this example shows another useful idea. Sometimes you don't need the full second level. For some setups, level 1 is already enough. That means you only need 4 coefficients per channel instead of 9, meaning only 1 float for attribute. It's just a different trade-off, and for some setups it's very practical one. So that's it with the practical overview of the system. You have generators and calculators to create the field, then modifiers to reshape it, or analyzers to inspect it, and rendering tools and materials to actually use it in a scene. In the next part, I'm going to build one example from scratch, step by step, but I will record that section on an old-fashioned way in one take with no editing, so sorry in advance for some pauses, slips, or clumsy wording. Okay, see you.